Hello, this is Sumner Strom. This is, I guess, my proof of being me. Yeah, I'm not recording with a software that's compatible with um, a camera right now. So, yeah, this is my physics circular motion test, as it says up here. I'm just going to be solving this problem, question 10.4. Okay, first look for the variables. We have this, and this. So, what are we trying to find? Maximum speed of the car without breaking the fish line. So we're trying to find velocity. So find velocity equals question mark. Known, we have so theta equals 30 degrees, mass equals, give me 1 second, 0.4 kilograms, radius equals 1, and yeah, Tmax equals 5. So part 1, we're trying to identify we're trying to get this. We're trying to get velocity. So part 1, we should just identify how we're going to get that. And so since it's circular motion, we're going to use this equation, mv squared over r. So centripetal force equals mv squared over r. And now, so what we want to do is we want to identify, since we're just trying to find velocity, we want to identify what this is. So what force centripetal, if you go back to this, you can see that too fast, so if it goes too fast, so that would be, without anything on it, that would just be the normal force holding it down. So the centripetal would equal to the normal force initially, but with the fishing line, it would be plus tension because you have another set, so it has to go the speed to surpass the normal force and the speed to surpass the tension. So you would have to also do this. So this is what we're trying to find, but we can substitute that to equal mv squared over r equals force met plus t. And if we want to, we can simplify that even further, but we do not need to for now. This is what we need to find. So our first thing we need, well, we already know tension, we already know mass, we already know the radius. All we need to find is this variable, is normal force, and what the normal force would be before it surpasses the certain amount to get that. So to do that, this is part 2. So what we first need to do is we're going to draw a little picture of the acting forces. I'm going to actually redo that. Okay. Pretend this is perfectly on scale, and my drawing skills are a lot superior than they are actually. So the normal force of this object, which is this, and so what we first, boom, 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 boom. So what we first need to know is we need to identify that this 30 incline is equal to you can see this. It's equal to this right here. So what we're trying to find, right, is this thing right here, this vector right here, this force vector right here. And so what we do know is we know this angle, because it's equal to this, which is the, if we go all the way back, it's equal to the banking angle. So that's 30 degrees. And then what else do we know is we know mg, because g is a constant. So we know this which is mg. And now we need to find the individual components. So what we're trying to initially find is we have this. Now we want to find just this alone. So we'll find this first. We'll find this first, which will be, we'll just keep it in this variable form. So it would be, since this is an opposite, and we have and we're trying to find the hypotenuse, we would first do, we have this, and we're trying to find the, this other part. We'd first get that mg times something times sine or cosine. It would be cosine. Right, no. It would be sine, mg times sine. Wait, frick. I'm sorry. Okay, so it would be, so the normal, so we would have force normal over n equals sine theta, because that would be this side over this side. So what we can do is we can, if we're just trying to isolate this, we can just use n sine theta equals normal force. And so now we just have to solve for n, which is this. Wait, no, that's that. We have to sign for this, which is another component. So then n, well, we know that, you know, it has to be cosine. So cosine right here, it would have to be something cosine. I meant to delete. So we would have this n cosine theta, because we also have the hypotenuse, equals mg. Because, so that would just be that this equal this angle, or mg, so this would be adjacent over theta, adjacent over cosine theta. So we would know that cosine equals mg over n. So then we just solve that, and we put cosine theta mg over cosine theta equals n. And with that, we can substitute back in n, because we're just taking this component using trigonometric identities. Okay, so then we have n, but we don't have n anymore, so we can just substitute mg over cosine theta multiplied by sine theta equals normal force. So if we get this, we can just get mg sine theta over cosine theta equals normal force. And then with that, we have mg tan theta equals normal force. And in this final part, all we're doing is we're combining. So we have this function and the other function, and now we have normal force. So we can make this mv squared over r equals force normal, which is no longer force normal. It's our new identity, which is mg tan theta. And then we have to add tension, as we did earlier. Now we can just do some algebraic manipulation, and we'll get, so we'll take the r, so r mg tan theta plus t equals mv squared. So then we just divide this all by m. So r mg tan theta plus t divided by m equals v squared. Now we can just square root it, and we'll get v equals the square root of r mg tangent theta plus t over m. And now all we need to do is plug in the numbers. So if we will get, so plug in the numbers, and you'll get so you'll get 1 for r times mg, which is 0.4 times 9.81 times 9.81 times tangent of 30 plus t was the 5 in the beginning over 0.4, and this will get us, and this will come out as, I mean, we can do some, we can eliminate r because it's 1, but this will come out as velocity equals 4.26 meters per second. Yeah, thank you for watching.